So last time we were discussing this Pittman-Stanley polytope. Which was given by these inequalities. So this was the inequality description, and we also showed how to express it as a Minkowski sum. Of little simplices like this. Okay. And I remind you that this delta, so I in square brackets represents delta of the set from 1 up to I, and this is just the convex hull of the first I basis vectors. Okay. And well, I drew one example because that's about as far as I can go. Actually, you could draw PS4 if you're very careful. But PS3 looks like this. We did it carefully last time. Okay. Now, then the next thing that I discussed is that if you wanted the volume of this Pittman-Stanley polytope, then what we needed to do is we have this mixed volume machinery, which allows us to express it like this. So we have to sum over all n tuples, n minus 1 tuples of numbers between 1 and n, all of those mixed volumes. Okay? But then the really nice result that we proved last time is that those mixed volumes are all very, very nice and explicit because they're basically either 1 or 0. I guess 1 over n minus 1 factorial or 0. So we said this is 1 over n minus 1 factorial. When you had a parking function, a reverse parking function, and 0 otherwise. And I'll remind you what a reverse parking function is in a second. But before I do that, what you'll notice right away is that basically then what we have here is 1 over n minus 1 factorial times the number of ones that appear, right? The number of reverse parking functions. Reverse parking functions of length n minus 1. Okay? And so this is our first formula for the volume of the Pittman-Stanley polytope. And it's a combinatorial formula in the sense that it just says if you're able to count these reverse parking functions, then you're going to be able to say what the volume is. Right? And let's quickly remind ourselves what a reverse parking function was. So definition, a reverse parking function A1 up to AN of natural numbers is a sequence with all these numbers between 1 and n having at most k elements less than or equal to k for all k. Right? And so maybe I'd like to list out all the parking functions of length 3 like we did last time. So here we need at most 1, 1, at most 2 1s and 2s, and at most 3 1s, 2s, and 3s. Right? And so then we said that these were the possibilities. We listed them last time. So it's 1, 2, 3 n-th permutations. Then we said we basically are allowed to increase coordinates here. So you could have 2 to 3 n-th permutations. You could have 2, 3, 3 n-th permutations. You could have 1, 3, 3 n-th permutations. And 3, 3, 3, which has no non-trivial permutations. Okay? So these are all the parking functions of length 3. Now, so here's an equivalent description. Equivalently, if we reorder the numbers to be j1 less than or equal to j2 less than or equal to so on less than or equal to jn, okay? So if you just take the whatever parking function you have and you put it in increasing order, then what you need is that the first number should be at least 1, the second number should be at least 2, this is and so on, okay? Then j sub k should be greater than or equal to k for all k. All right? So that's a reverse parking function. And what I would like to do today is show you some of the beautiful combinatorics of parking functions. So I want to tell you, first of all, why they're called parking functions, and also what can we say about them, okay? And the first thing that I'll tell you right now is that they are very, I wouldn't say easy to count, but the answer is very easy. So here's a theorem. There are exactly n plus 1 to the n minus 1 parking functions, reverse parking functions. Of length n. Okay? So for example, what this says here is that the number of parking functions of size 3 is 4 squared, right, which is 16. And if you count these, 5 plus 3, 8 plus 3, 11. I'm getting nervous already. 6. This is always the hardest thing. 6 plus 3, 9 plus 3, 12 plus 3, 15 plus 1, 16. Okay? So here it's true, and this is true for any value of n. Okay? And I hope you like this result, because we saw this number last week, but we saw it in a very different context. as counting the spanning trees of the complete graph. Okay? And here they appear again. So the corollary of that result is that the volume of the Pittman-Stanley polytope is simply 1 over n minus 1 factorial times the number of reverse sparking functions of length n minus 1, which is n to the n minus 2. Okay? Which is a nice, simple, beautiful formula for that volume. Okay? Now, I don't know, what's your first reaction when you see this formula? And I hope you're amazed. I hope you think it's beautiful. But does it ring a bell? So I think what you're telling me, Dito, is that this number came from spanning trees, and then you're kind of saying, are you reordering the spanning trees or something? What is this really doing? How did spanning trees come up? If you remember, we counted spanning trees so that we could find the volume of the permutahedron. And do you guys remember what the volume of the permutahedron was? If you look back, you'll see that it's exactly this, but without the factorial. So maybe let me erase this because we don't need this anymore. The volume of the permutahedron is n to the n minus 2. Okay? And I actually had never seen these two things next to each other. So I knew both results, but I had never kind of thought about them the same day. But I prepared this class, and then I prepared this class the same day, and I thought, wow, that's really interesting. You kind of want to say that this polytope is n minus 1 factorial times this one. Okay? And if you think about what pi 3 looks like, the third permutahedron is just a hexagon. It's a regular hexagon. Okay, and you know, you see it. It's exactly 2 copies of the Pittman-Stanley polytope. Okay. So then I have an open problem for you, which is do this for any dimension. And I looked it up, and I don't think anybody has done this, but I think one of you guys should do it. So here's a question, open problem. I don't know. I've never seen this before. And so, is it possible to cut up the permutahedron into n minus 1 factorial copies of the Pittman-Stanley polytope? I don't know. I mean, we don't have a lot of evidence. We just have the third example. But if you're an optimist like I am, then you think this must be possible because, I mean, it is an optimistic hope. I would say that this is little evidence, but I am an optimist. So I think this might be true. And one reason that I think it might be true is that actually the inequality description of this guy is kind of similar to the other one. So that's what makes it seem plausible to me. But I don't know. Okay.
It's an easier question for people who haven't thought about it. How fast does that function grow? 1 over n minus 1 factorial.
Have you thought about it? How big this number is, 1 over n factorial? Or do you know how to do it? I mean, about how big is n factorial, basically? So really, really big, right? But you know, how big? How big? I always forget exactly what Stirling's formula says, but is it 2? There's a You're on the computer. Why don't you Google for me Stirling formula? While you're at it. I know it has a square root of 2 pi, but isn't it n over n halves?
There's an e in there somewhere.
I don't remember. It's n to something over e to the n.
Yeah. Okay, so it's the square root of 2 pi n.
To the n, right?
Quantity n over e to the nth power.
Okay. Okay. So this is Stirling's formula. And factorial grows like this. So it grows like n to the n, basically. Except for the square root of n. That's interesting, actually. I hadn't thought about that either. That this is basically n to the n, and it's off by a factor of square root of n. And it's off by an n that's missing from there. So I think this grows like square root of n as a function of n.
Well, no, there's an e to the n.
Sorry, e to the, yeah.
So it's e to the n.
So it's e to the n and then some little constant. Yeah. So this volume is going to be exponential, like e, basically. So it's almost like having a sphere of radius e, I guess. It's kind of interesting. So I mean it. I really think one of you guys should do this. Okay. So let's prove some things here. So before we prove anything, why reverse parking function? So this is an interesting story also. So why reverse parking function? Well, the reverse is not too interesting. Generally, the parking functions that people think about are kind of the reverse of these, but that's not a big deal. But why parking function? So the question goes like this. Imagine you have, actually, this comes from a paper that is very un-PC. So this paper is called The Problem of the Capricious Wives. It's a good thing that we don't have any such things anymore. But in the problem of the what you have is that you have this street, and you have a bunch of stores along the. I'm not kidding. This is really this is really what the paper says. So you have this street, okay, and then you have all these shops here, and it's a one-way street, and there's parking spots here, and there's exactly n parking spots. Okay, 1, 2, 3, and 4. Let's say n is 4, and then n people are going to come in and try to park. Okay, so there's n cars. So there's my best rendition of a car. And each car has a preferred parking spot in front of the store that the capricious wife wants to go to. I think, let me just drop that. I really just, this is nonsense. Point is that every car has a preferred spot, okay? So preferred spot 3, preferred spot 2, preferred spot 3, and preferred spot 4, okay? And so then these cars are going to come in and try to park. Okay. Each car tries to park in their preferred spot. Preferred spot. And if that spot is not available, then they're going to take the next available one. If busy, take the next available one.
By next, you mean here? Or?
It's a one-way street, so you just, I mean, okay. As you would do, you would just try to park as close as possible to where you wanted to park. Okay. So let's say that let's number the cars. Okay, so this is car 1. Actually, maybe it's more useful if, well, okay. Car 1, car 2, car 3, and car 4. Okay, and these orange numbers we're going to call A1, A2, A3, and A4. Okay. So then the cars come in. Okay. And so what happens? Let's see. So the car number 1 goes to spot 3 and takes it. Right. So this becomes 1. Okay. Then this car tries to park at 2. Okay. And it succeeds. So this is car number 2. Then this car tries to park at spot 3, but that's busy. So then it tries to park here, but that's busy. So then takes this one. Okay, so this is car 3. And then car 4 wants spot number 4, which is free. So car 4 parks there. Okay. And the statement is that this is going to work out if and only if this is a reverse parking function. And you see that 4, 3, 2, 3 is a reverse parking function. And the statement says, the proposition says that because it's a reverse parking function, everybody managed to park. But if it wasn't a reverse parking function, then this wouldn't have worked out. Okay. So is it clear what the statement is that I'm making? So okay. So proposition. All cars can park if and only if A1 up to AN is a reverse parking function. Okay. And so now I can tell you really what I mean by reverse, because you see that the way that I numbered my spots was from right to left. Okay, and people normally number them in the other direction. And so that's what people normally call parking functions. Okay. So let's prove this. This is easy actually. Proof. So first let's prove this direction. Okay. Suppose that all cars parked. Then if you look at the parking spots k minus 1, 2, and 1, they're all busy. Okay. But then what? See, the problem is that I prepared class with parking functions, and now I'm teaching class with reverse parking functions. So I might need your help. All cars parked. Okay. Every car found a spot.
Right before it left the sequence of shots.
Uh-huh.
That means that is ordered.
I mean, you basically see it, right? I'm going to turn the argument around a little bit in a way that I can think of right now. Okay, which is so instead of 1 to k, let's look at spots n to k, which is what I would need to reverse it, up to k plus 1. Okay, these spots are taken, and they must be taken by people with preferences greater than or equal to k plus 1. they're taken. So, and they're taken by people with preference greater than k. Okay, so we have n minus k spots taken by people with preferences greater than k. And that means that you have at least n minus k preferences bigger than k, which means that you have at most k that are less than k. So you have at most n minus k preferences bigger than k, which means that the other ones, at least, let me turn around this whole class, but at least n minus k preferences less than k, greater than k, which means at most k preferences less than or equal to k. Okay? That's the argument. So if everybody parks, I must have a reverse parking function. Okay, now let's go in the other direction. But we'll do it with the contrapositive. So suppose that some car couldn't park. Some car couldn't park. Okay. Let's say that spots 1, 2, up to. Let me do it. Let's just draw it in a picture. Suppose some car couldn't park. Say when they arrived, we had this situation where 1 was full, 2 was full, k was full, and k plus 1 was empty. Okay, so empty, and all of these are taken. Okay, and this car comes in, it's trying to park. And this car could not park. How could that be? Well, because this spot is empty, that means that none of these cars wanted a spot bigger than k plus 1. So all of these cars, all of these k cars have preference less than or equal to k, because if they had a preference bigger than k, they would have taken this spot. Okay? And if this car cannot park, that means that it must also have preferences, a preference less than or equal to k. Preference less than or equal to k. And so between these and these, I have k plus 1 preferences less than or equal to k, and that means that I'm not a reverse parking function. Okay? So that's the argument. Okay. So then this is why we call them reverse parking functions. And this is going to be what allows us to prove this. Okay? I should tell you, there's many proofs of this result. I told you one thing combinatorialists like to do. When we have two questions with the same answer, one thing we can do is find a bijection between them. So for example, one proof of this would be to find a bijection between the parking functions of length n and the spanning trees of k n plus 1. Okay? And that can be done, and it's actually a little bit tricky, but it can be done. Okay? But the proof that I'm going to give you for this is my favorite proof, and it actually uses the car interpretation. Okay? So here's the proof. let's consider the parking problem. But we're going to change the road a little bit. Okay, so now this is going to be kind of a circular mall instead. So the cars are going to come in, and then they're going to try to park, but then the road looks like this. Okay. And the parking spots are going to be here. So this is spot n minus 1, n minus 2. Okay. And I'm going to add a parking spot. And I'm going to call it 0. Okay. But I'm considering exactly the same problem, except I'm just changing the road. So you have n cars, okay? 1 up to n. And then these cars are going to come in, and they're going to try to park. And this is a one-way street, and it goes clockwise. Okay. So the cars can only go clockwise. And basically what they're going to do is that they're going to try to take their spot, okay? But then if that spot is not available, they're going to keep driving until they find a spot, and we're going to allow them to circle around if necessary. Okay? And so that's more generous because that means that everybody's going to get to park. Okay? Because there's n plus 1 spots, there's only n cars, so everybody's going to get to park eventually. Okay? So preferences are now between 0 and n. So you are allowed to prefer the spot 0, which you weren't before, right? This spot didn't exist. Preferences are now like this, and cars are allowed to circle around. So in the end, everybody parks. Okay? So how many parking preferences are there? For each one of these cars, you just say what's the preferred spot. Okay, so for this car, there's n plus 1 spots. For this car, there's n plus 1 spots. For each car, there's n plus 1 choices. So I have n plus 1 to the n. Possible parking preferences. Okay. Which looks a little bit like what we're trying to go after. Okay, so that's where you see that we might be headed in the right direction, although this seems very strange to change the rules of the game. But you'll see why I do that in a second. Okay. So the plan is the following. I'm going to say suppose that if your preferences are A1 up to AN, then let's say that, I don't know, that car I parks in spot, I don't know, let's call it BI. Okay? So if the incoming preferences are A1 up to AN, then I'm going to say that the outcome of this procedure is that car 1 parked in spot B1, and so on. So I'm basically labeling B1 is the spot where 1 parked, B2 is the spot where 2 parked, and so on. Okay? So let's think about this now. What if the preferences were A1 minus 1 up to AN minus 1? Okay. So what if everybody changes their mind and now they don't want the spot that they were after but the next one? So think about it. What happens? Okay, well, first car 1 comes, and then instead of going to the spot they wanted, B1, they're going to go to the next one, B1 plus 1. Okay. Then the second car comes in. Okay. And, I mean, my point is basically that if you shift everybody's preferences by 1, then it's just kind of rotating the whole picture by 1, and everybody's going to turn up to take the spot next to the one that they had. Does that make sense? It's just kind of like the same movie but replayed a second later, a parking spot later. Okay. So the point is that now car I parks in spot B I minus 1 like this. Okay. Now, there is one thing that we have to be a little bit careful about here, which is what if somebody preferred the spot 0? What does 0 minus 1 mean? Well, it should mean n. What else could it mean? If you're in a circle, then you should be thinking that this is a cyclic additive group, and minus 1 equals n. Okay? So here we're going to be doing everything mod n. Okay? Well, n plus 1, sorry, because we have n plus 1 spots. So minus 1 is equal to n. Okay? Okay. So then what if the preferences are A1 minus 2, okay, up to AN minus 2. So if you shift the preference over by 2, then naturally the same thing happens, but you're going to get BI minus 2, and so on. Okay? How far can I take this? Well, this is a cyclic group of order n plus 1, so I can only do this n times. And if I do it n plus 1 times, then A1 minus n plus 1 is going to be A1 minus 0, and I'm going to be back where I started. And this should be familiar to you. That I'm clearly doing some kind of group theory coset argument here, right? These are kind of like the cosets of this group. Okay. Now, what's my point? My point is that no matter what preferences you have, if you have n cars and if you have n plus 1 parking spots, then there's going to be exactly 1 slot open. Okay? So let's call that slot. So 1 open slot, and let's call it, what letter haven't I used? B. Okay? No, C, how about C? Or S for slot? So 1 open slot S. Okay, so the preferences A1 up to AN lead to 1 open slot S. So then what's going to happen when you shift the preference over by 1? Well, the empty slot is also going to shift over by 1 because everybody's parking spots shifted over by 1. So here, the open slot is S minus 1. And here, the open slot is S minus 2, and so on. And here, the open slot is S minus N. Okay? And now, the very simple observation that I'm going to make is that exactly one of these numbers is 0. Right? Because these are all the n plus 1 numbers mod n. So we have exactly 1, 0. So I don't know. Let's say that this is 0. What does that mean? We have a bunch of parking preferences that left the spot 0 open. Okay? And if the spot 0 is open, being the last available spot, that means that no one ever needed to get there. Okay? It means that this slot never came into play, and we're exactly in the previous situation. Okay? So that means that those parking preferences must lead to a solution to the other problem with the street with no circle on it. Yeah? So that's the nice, clever argument. This brings it back to where it was, and it says that exactly if this is a 0, then these preferences are a solution to the previous parking problem. Okay? This is a solution to the previous parking problem. In other words, this must be a reverse parking function. Okay? Whereas these other ones cannot be a reverse parking function because they use the slot 0. Okay? And so what did I just do? I took this set of size n plus 1 to the n, okay? The set of all possible preferences, and I split it up into families of n plus 1 in each family. So here I have a family of n plus 1 preferences. And I'm saying that out of these n plus 1 preferences, exactly one of them is a reverse parking function. Okay? So then what that means is that exactly 1 over n plus 1 fraction of the preferences is the number of parking functions. Okay? So let me just write it out a little bit more carefully. That means that the number of reverse parking functions is 1 over n plus 1 times the number of total parking preferences for the circular road. So it's 1 over n plus 1 times n plus 1 to the n, and so it's exactly what we wanted. Okay. That's the proof. It's a nice it's a nice proof that shows that actually there is some kind of cyclic structure that's hiding here, and it's a little bit confusing because it's cyclic of size n plus 1 when the functions are of size n. So that's why it's a little bit hard to see it, and to really unveil it, you have to change the problem around a little bit. Okay. But that's the proof. Do you guys have any questions about it? Okay.
So is the objective proof with the spanning trees by any chance?
So the question is whether there is a bijection between the parking functions and the spanning trees, and the answer is yes. And I can't think of one offhand, but I mean, if we were in homework time, this would be a homework problem. This would be a nice homework problem. You should think about it, and I'm happy to also help you think about it. And also, I mean, I do know a paper that has that bijection with a bijection with a lot of additional properties. So I can point you to that if you're interested. There's a paper of Stanley that has the words parking functions in the title, and that one has a bijection like that. Okay. There's something else that I'd like to point out here. So these are the parking functions of length n. And these also separate very nicely into families by column. We talked about this last time, that it might seem counterintuitive at first that whether you're a parking function or not is independent of what order you're in. Okay? So, in other words, it does. I ordered the cars driving into the mall here, but I didn't need to do that. The point is that whether the parking situation worked out or not was independent of what order I put the cars in. It only depended on the preferences. Okay. And in other terms, what I can say basically is that I can split the set of parking functions into equivalence classes. Okay, where two parking functions are equivalent if they're permutations of each other. Okay. And combinatorics like to count everything, so we should also count the number of equivalence classes, not just the total number of parking functions, but how many families do they come in. Okay. So call two parking functions equivalent if they are permutations of each other. Then, what is the number of equivalence classes? Okay. Well, one way that you can do this kind of thing is if you can identify a canonical element of each equivalence class that is your favorite. So what is your favorite element of each equivalence class? Well, here there's a natural choice, right? So it's natural to just say my favorite is just the increasing one. Or okay. And so this is equal to the number of non-decreasing reverse parking functions, right? And if you notice, what I'm saying is exactly what I said over here. Okay, in the second criterion for what a parking function is, I said put it in order, and then check that the first number is bigger than 1, the second is bigger than 2, and so on. Okay, so this is the same as the number of sequences of numbers j1 up to jn between 1 and n such that jk is bigger than or equal to k for all k. Okay. And so this is what we need to count. And well, let's do an example. How about something like this? 2, 3, 3, 5, 7, 7, 7, 9, 9. Okay. So I need to check that that the numbers are bigger than or equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9 respectively. And they are. I want to count these things, and it turns out that there's a very nice graphical way of representing them. Let me make a board of size 9 by 9. Okay, so there it is. Now let me put the numbers here: 2, 3, 3, 5, 7, 7, 7, 9, 9. And then what I'm going to do is that in each row I'm going to color as many cells as this thing tells me to do from left to right. So here's 2 cells, 3 cells, 3 cells, 5 cells, 7 cells, 7, I'm going to run out of ink here, 7, and then 9, and 9. Okay. And you can clearly see that this makes a nice shape here. Since we're fond of staircases, and here's a nice staircase, right? Okay. Now, what property does this staircase have? The point is that you need to have colored at least 1 cell here, at least 2 cells here, at least 3 cells here, at least 4 cells here. So that has the property that you cannot go below this diagonal. Okay. So here's the diagonal of the board. Okay. And I think you'll agree that this is a bijection. Given numbers like this, you can get a path that never crosses the diagonal. And given such a path that doesn't cross this diagonal, just color it in and see how many cells you colored in each row, and you're going to get this back. Okay. And so really what you're counting is the number of such paths. And maybe, I mean, if you've taken some combinatorics class, you must have seen this. And these are called either Dick paths or Catalan paths. And the answer to this is the Catalan numbers. It's like the answer to everything is the Catalan number. By the way, so I've never read this book where the answer to everything is 42. But 42 is a Catalan number. I don't know if you realize this. So even the answer to that is a Catalan number. This is okay. So and this is a theorem. Okay, and I think I ran out of time, so I'm not going to prove it. But once you have it in this form, and if you know what Catalan numbers are, I mean, we discussed what they are